Good evening. The continuation of the previous series. Today we are going to discuss on two-ray reflection model. What is two-ray reflection model? It is otherwise known as two-ray ground reflection model, which is a simplified propagation model commonly used in wireless communication to analyze the effects of ground reflection on signal propagation. It provides a straightforward method to estimate the received signal strength at a receiver located near the ground when there is a clear line of sight LOS between the transmitter and the receiver, as well as the reflected signal from the ground. There are key features of a two-ray ground reflection model so as to have a good understanding. The first feature is direct path and ground reflected path. The model considers two paths as shown in the figure here. One is direct path, which is direct line of sight from the transmitter to the receiver, whereas the another one is the reflected path, which once hit the ground and reflects back to the receiver. These are the two parts that the signal takes from the transmitter to the receiver. Direct path is the signal travels directly from the transmitter to the receiver without any reflection or disturbances. Ground reflected path, the signal reflects off the ground before reaching the receiver. Next key feature is path length. The direct path and the ground reflected path lengths are different due to the geometry of propagation environment. However, for simplicity, we'll assume the two-ray ground reflection model. Assume that both parts have the same length just for easy analysis. We are assuming so, but practically those two paths are not of equal distance. Next is phase relationship. The direct and the reflected signals may have different phases depending on the path lengths and the relative position of the transmitter, receiver, and reflecting surface. In some cases, the direct and reflected signals may be in phase and reinforce each other, while in other cases, they may be out of phase and particularly cancel each other. This can be easily represented as constructive signal or deconstructive signal. Path loss calculation is another important feature to be considered. The received signal power is calculated as the sum of the powers of the direct and the reflected lengths, considering their respective path losses too. The path loss for each path is typically calculated using a propagation model such as Friis transmission equation or the free space path loss. Taking into account the distance between the transmitter and receiver, some use cases are there. The two-ray ground reflection model is particularly useful for analyzing wireless communication systems and also such as cellular networks or point-to-point microwave links, where the receiver is located close to the ground and ground reflection significantly impacts signal propagation. While the two-ray ground reflection model provides a simple and nutritive framework for understanding ground reflection effects, it is a simplified approximation and may not accurately capture all the complexities of real-world propagation environment. Practically, more advanced propagation model and measurements are often used for detailed analysis and system design. So, how the analysis has been done in ground reflection model or two-ray model. In mobile radio channel, single direct path between the base station and the mobile is seldom one physical means for propagation. Free space model is a standalone and inaccurate. Two-ray reflection model is useful based on the geometric optics. Consider both the ground reflected path and the direct path, reasonably accurate for predicting large-scale signal strength over several kilometers apart from the transmitter to the receiver. Let us assume the height of the transmitter is more than 50 meters. See here, this is a simple example or a representation for a transmitter and receiver kept 50 meters apart. The transmitter is of greater heights when compared with the receiver. Height of the transmitter is represented as ht. Height of the receiver is represented as hr. There is a direct path ELOS and reflected path E incident and E reflected. Those two rays form an angle with respect to the ground. The total path is equal to direct path plus reflected path. E total is equal to E line of sight plus EG or ER. So this is mentioned here. E total is equal to E line of sight plus EG. EG is nothing but ground reflected path. Let E naught be the E at reference point D naught. D naught is nothing but the reference point. Therefore, E of D of distance T is equal to E naught D naught by D cos omega C T minus D by C, where D is greater than D naught. These are the expressions we have gone through in the previous subject, electromagnetic fields. So we can have that reference as E line of sight, D of T is equal to E naught D naught by D cos omega C T minus D dash by C. And similarly, Eg of D double dash of T is equal to reflection factor E naught D naught by D double dash cos omega C T minus D double dash by C, whereas E total is equal to E total, which is dependent on D comma T, is equal to E naught D naught by D dash cos omega C T minus D dash by C plus reflection coefficient E naught D naught by D double dash cos omega C T minus D double dash by C. So after further simplification, the result is E total D of T is equal to the magnitude E naught D naught by D cos of omega C parameter plus of minus 1. Here the reflection coefficient is considered to be minus 1 and the entire parameter E naught D naught by D double dash cos of omega C T minus D double dash by C. So this represents the mirror images. We have studied the same topic in the previous subject, electromagnetic fields. Assuming the ground as a medium, and below the ground there is a image falls below the ground, which is nothing but the mirror image. And next topic is path difference. Path difference is nothing but the distance between the direct line of sight path from the transmitter to receiver and also from the transmitter to receiver for the reflected path, right? So del is equal to D double dash minus D dash. Obviously D double dash will be, that is the ground reflected path will be much greater than the reflected path. Therefore, from the previous diagram, we can infer and write the equations like ht plus hr the whole square plus d square minus ht minus hr the whole square plus d square. And after continuous simplification, the path difference del becomes 2ht hr by d. So this is the final path difference. Next topic is diffraction. And diffraction is nothing but it is the bending of wavefronts around an obstacles. As the reflection happens, whenever the medium it hits is a smooth or reflective surface, the reflection phenomenon can be understood. Similarly, diffraction occurs when the waves hit on sharp edges or obstacles. Diffraction allows radio signals to propagate behind obstructions and is thus one of the factors why we receive signals at different locations where there is no line of sight from the base station. It is simply named as bending of waves. See here in this picture, you can easily understand. When the wave hits the sharp edge of the tower, it forms a number of wavefronts. These are the wavefronts, right? The curved picture shows the wavefronts. So each wavefronts are formed due to the hit of the signals exactly at the sharp edges. Once the waves hit the sharp edges, it gets scattered or secondary waves are generated. Many number of secondary waves are generated. So this is nothing but the wavefronts. Although the received signal strength decreases rapidly as the receiver moves deeper into an obstacle's shadowed region, the diffraction field still exists and often has sufficient signal strength to produce a useful signal. So this picture shows the tower, the propagation. Once the diffraction occurs, the waves start bending. This picture clearly replicates the way of propagation, how the wave gets influenced due to diffraction effects. Thank you.